What are we talking about? The second derivative test. That's what. So let's do it. Kablow. Oddly enough, the second derivative test is a test to find max and mins. So the second, let's write that down here. Second derivative test finds maximums and minimums of a function. Finds max and mins of any function. I'm going to say f of x, but it doesn't matter if it's f of x or not. Just some function. Now, the reason I think that's weird is because that we use the second derivative to find concavity, concave up and concave down. So I don't know, I always thought the second derivative test should be a test to find concavity or points of inflection or something. But it's really to find maxes and mins. And here is the main reason we have it. All right, I'm going to make up some example here. Okay, let's say we have, let's think back to our days doing implicit differentiation, and say this is, I don't know, equals 9. Now, this curve right here, it's a nice curve. There we are. You know what? I'm going to change this from 9 to make this a little bit easier on myself. Let's make it 25. There we go. That's just a circle with a radius of 5, right? So 5, 5, 5, all that stuff. And we know the point 3, 4 is on there. So over 3, up 4, like maybe, I don't know, right here. The point 3, 4 is on there. Now, let's pretend, not the point 3, 4. My God. The point 5, 0 or 0, 5 is on there. There we go. Let's pretend for a second we did not know what this graph looks like, okay? So this is over here, but let's cover that part of the screen, divert your eyes, I don't know. Let's pretend you don't know what that graph looks like. And your question is, determine where the maximums of this function are, okay? Well, if you need to determine where the maximums of this function are, again, you don't know where the circle, you don't know this looks like a circle, okay? Pretend you're a completely, young child, and you have no idea this looks like a circle. Well, you're in calculus class as a young child. You don't know it's a circle, but you know calculus. And you know the way you find maximums is you derive it and find where the derivative is 0 or undefined. So let's go ahead and do that. 2x plus, remember we're deriving with respect to x here, so implicitly we're going to get 2y dy dx. That's going to be equal to 0, which means the derivative dy dx is negative 2x over 2y, which is negative x over 1. Now, even though there's an x and a y in this derivative, all of our rules for derivatives still apply. Now, what that means is this is going to have critical values where the derivative is 0 and where the derivative is undefined. And since it's a fraction, this thing's going to be 0 when the numerator is 0. So when x is 0. And you can see, now again, let's go back and pretend we do know what the graph looks like over here. You can see when x is 0, we have these 2 points, up here and down here. This one's a maximum, this one's a minimum. So there's two critical points there from our one critical value of of x equals 0. The reason that's happening is because this is an implicit equation. So this isn't a function. Functions cannot have 2 critical points at one critical value. Then it wouldn't be a function, it wouldn't pass the vertical line test, but this thing can. Okay? Now this thing's undefined when y is 0. Well, when y is 0 on our equation, if y is 0, then x would be positive or negative 5. So that would be these 2 points here. So those are also critical values, but we're not going to talk about those for right now. Okay? My main question is this. If you're given this function, x squared plus y squared is 25, you don't know what it looks like because sometimes you don't know what equations look like. How are you going to find out where a maximum and minimum would be if we've got an x and a y in there? The reason this doesn't work out is let's do what we usually do here. So I'm going to erase all this stuff. What we usually do is we find our critical values. Well, our critical values are x equals 0 and y equals 0. All right, now I don't want to mess with y, so let's ignore him. Let's just look at the x equals 0 part. Well, normally we would make a number line, so y prime, and we would try to determine what happens to the derivative on either side of 0. But when I try to plug an x value into my derivative, like negative 5, well, now I don't know what this derivative is going to equal because I've got a y value there as well. So this is me trying to do the first derivative test up here. That's what this is. I'm trying to determine what the derivative is doing when it passes through 0. Is it going from positive to negative? Is it going from negative to positive? The reason that we can't do that right now is because there's a y in there. And if you look at our graph over here, there's 2 points at 0. One up here, one down here. One's a max and one's a min. So Not only do we need to know the x value, we also need to know the y value. Well, that's not really a problem. Let's go back up here. This was the original equation. X squared plus y squared was 25. We know we're dealing with x is 0, and if x is 0, that means 0 plus y squared is 25, which means y is positive or negative 5. So there's 2 points on this graph that we're interested in at x equals 0. They're over here, you can see them. But we just found the y value. 0, 5, and 0, negative 5 are critical points. So we've solved the mystery, we found the y value. Okay, let's box this guy off too. Critical points. We solved the mystery, we found the y value. There's 2 points there, great. So now let's go back to our number line. Well, when x is less than 0, what's this going to be? Well, since there's 2 points, it's really hard to determine that. We could plug in y would be 5, but then x would be 0, we get 0 back. There's nowhere for y to be plugged into this number line, is the problem. So the first derivative fails here. Not doesn't fail, the first derivative test fails here. So we need some other way of determining if there's a maximum or minimum here. Well, we know something weird's going on. There's a critical point. Here's how we do it. This is what the second derivative test says. We'll go to the next page, add a page. Second derivative test says this. If f prime at some number is 0 and f double prime at that number is less than 0, so let's think here. F prime is 0. That means the function is flat, whether it's got a horizontal tangent, whether it's a max and minimum, or like a little curvy guy like that. Okay. But we're also saying f double prime at that same point is less than 0. Well, if f double prime is less than 0, think back to what that means. F double prime negative means the function's concave down. So if f prime is 0 and f double prime is negative, that means this function at that point must look like that. It must be flat. That's because the first derivative is 0. Concave down. Well, what is that? That is a maximum. I'll answer it for you. That's a maximum. And that's exactly what the second derivatives test says. If the first derivative is 0 and the second derivative is negative, then there's a maximum at that point. Maximum at the point C, f of C. And if f prime of C is 0 and f double prime of C is positive, well, now that's a concave up function with a horizontal tangent. That is a min at the point C, f of C. Okay? And maybe you're thinking, well, Mr. Smith, what happens if one of these guys is undefined? Well, then the second derivative test does not tell us anything. So be careful about that. If the first derivative is undefined, there's still a critical point there. You just can't use the second derivative test to determine if it's a min or a max. You got to use the first derivative test. So no biggie. Just sometimes you have the option of using the second derivative test, and sometimes you are forced to use the second derivative test. And that's what's happening in this example I made up back here. We can't use the first derivative test. There's a y in there. So generally, like on the AP exam, or if your teacher's like kind of a weirdo jerk and he gives you implicit functions and asks you to find the max and mins, you have to use the second derivative test. Or it's easier to use the second derivative test, I guess. So here's how we're going to do this. We know it's 0. The derivative is 0. Okay, we've already figured that out. Now we got to find out what the second derivative is. So let's go back here. Or that's not back here. Let's go to the next page. We said our first derivative is negative x over y. We've determined that there are critical points at 0, 5, and 0, negative 5. Now, we also determined that there are critical points when y is 0, but we're not going to talk about that right now because that's when the first derivative is undefined, and our second derivative test does not tell us anything about the first derivative being undefined. I just want to look at the points where the first derivative is defined, 0. Now, let's go back. You should be able to see here 0, 5 is a max, 0, negative 5 is a min. We already know that. So this one's a max just by looking at the graph. You probably think, well, why the crap are we doing this if I know what this is a max and a min already? Well, because we look at easy examples so that it gives us a way to understand harder examples. So what we're going to do is prove that it's a max using the second derivative test. In order to do that, we found out where the first derivative is 0. We got to find out the second derivative now. So d2y over dx squared is, doing the quotient rule here a little bit, derivative of the top is negative 1 times the bottom, y, minus the top, negative x, times the derivative of the bottom. dy dx over the bottom squared, y squared. Now, back when we did implicit differentiation, we had to simplify this whole nasty thing. But now we don't have to, because we're not trying to find the second derivative. We're just trying to use the second derivative to determine if it's positive or negative. Because, again, let's go back to our rule. If the second derivative is negative, what's going to happen is there's going to be a maximum. If the second derivative is positive, then there's going to be a minimum at these points, because f prime is 0. So let's go back. Well, I can just plug in the values. I know what y is for each point, so we actually have to test both points. Let's test this one first. Now we know there's a max there. We're going to show that the second derivative test works. We're going to plug in 0 and 5 for x and y, and we know that the derivative dy dx is 0 there, because when you plug 0 in for x, you get 0. So test in 0, 5. When we plug these in, we're going to get negative 1 times y, which is 5, minus x is 0, so negative 0, times the derivative, which is also 0, over y squared, which is 25. Well, this is negative 1/5. So at 0, 5, here's what we know. We know f prime at 0. Well, let's not write it like this. I know I've been writing f prime. Let's write in dy. We know dy dx at the point 0, 5 is 0. And we know the second derivative, d squared y at dx squared at 0, 5 is negative 1/5. We showed all that, so I'm going to erase all this junk. These two things combined, with our powers combined, tell us that there is a maximum at the point 0, 5 by the second derivative test. Easy enough. Now, you never really have to use the second derivative test unless you've got, again, like this implicit differentiation going on. It's much easier just to do the second derivative test than to try to figure out the first derivative test. So you derive it, you find what the second derivative is, and it lets you know if there's a max or a min. Remember, both these pieces have to happen. The derivative has to be 0, and the second derivative has to be negative, maximum. Over here, we can take our derivative, which is this guy up here still, to test the point 0, negative 5. Okay? So we need the second derivative at 0, negative 5. And that's just going to be plugging in. We're going to get negative 5 minus 0 times 0 over negative 5 squared is 25. That's going to be positive 1/5. So the second derivative is positive. The first derivative was 0. So by the second derivative test, there is a minimum at the point 0, negative 5. And again, you're probably saying, I already knew all this crap. Why am I still watching this guy talk about this curve? We just proved it, okay? Be happy. We proved it. There was a max here, and we showed that. There was a min at 0, negative 5. And we showed it by doing this second derivative test. All good? Now, it doesn't have to be implicit differentiation for this thing to work. You could use a regular old function, and that'll work too. So just to do a really quick one, let's do, for instance, y equals x squared. Another very simple curve. We know there's a minimum at 0, 0. We know what this curve looks like. Okay, but just to show you that the first or the second derivative test works again, y prime is 2x, and that is 0 when x is 0. So there's a critical point at x equals 0. Well, rather than doing my first derivative test, which would involve me making a number line for the first derivative and testing intervals, I could just find the second derivative, which is 2. Well, the second derivative is always positive. So here's what we know. Y prime at 0 is 0. And y double prime at 0 is 2, because it's always 2. And by these two facts combined, first derivative 0, second derivative positive, there's a max, oh man, a min at the x equals 0. When x is 0, we need the y value for this point. Well, anytime you need the y value, you plug the x value back into the function. 0, 0. Simple enough. I was going to say something else. I can't remember. So I'll save it for later. We'll do some examples and graphing and everything. Have a great day.